All right. It's great to be here again, and it's great to see a full room. Okay, so I'm going to be talking about logical relations, as Benjamin just said. So let me just sort of say a few things about setup and what the lectures are going to cover and things like that. Okay, so. So, as Benjamin said, logical relations are one of the most fundamental proof techniques that in programming languages, and you can use them basically for all sorts of things. And that's really, the amazing thing about them, that there's just a vast number of properties for which they're useful. So, just to give you some examples, one of the earliest uses of logical relations was to prove that all terms in the simply typed lambda calculus, all well-typed terms in the simply typed lambda calculus, terminate. So it's a proof that evaluation will always terminate in that language. They have been used to prove observational equivalence in languages. So why would you want to prove observational equivalence or equivalence of programs? Why would you want to prove that two programs are equivalent? Might that be useful? Reasoning about correctness, right? Like suppose you're doing some compiler transformations, right? And you want to show that the program that you had before you transformed it into something else, hopefully a more optimized version, that the two versions are equivalent, right? That they'll behave the same, they'll always give you the same answers. Some other examples, let's say you have two implementations of the same abstract data type, right? Like let's say you're implementing a stack using a linked list versus using an array or something. And you want to reason about the fact that you actually have two implementations that are equivalent. Maybe you started out with the less efficient one, and later on you wanted to plop in a more efficient one. So these are just examples of where you might use them. So equivalence is a big thing. But you also need them in security. And I'll say a little bit more about this later, and Andrew Myers will show you a use of logical relations in one of his lectures as well. But let me do a little bit more setup. One thing that I want you guys to remember is that logical relations essentially come in two flavors. And this is helpful, like mentally, to categorize them as such. There are logical predicates and logical relations. Basically, these are unary, as indicated by the word predicate, as opposed to relation, and these are binary. Okay, and there'll be a certain pattern that emerges during these lectures, which you'll start to sort of understand that this is how I want to set things up. Okay, so unary logical relations are used. What do you do? Okay, what is a logical relation? Well, logical predicates are unary logical relations. What you do is you basically say that the terms in your language satisfy a certain property, a certain predicate. I'll write P for that, and we basically say that E satisfies P, and we index this with a type. So a logical relation or a logical predicate says, you set up a definition of when all terms in the language of type tau satisfy this predicate or property of interest to P. Okay? Binary logical relations, you have two terms. So here I'll write R for relation as opposed to predicate, but you basically set up some sort of relation R, again, indexed by the type, and you say when expressions E of type tau, sorry, you set up a relation on E and E prime, right? So you have two terms. And you say that the terms E and E prime belong to this relation. So here, let's see. We could start talking about, this will be the general pattern of setting up a logical relation when you want to talk about a term E and E prime of type tau being equivalent to each other. Okay, so equivalence is normally, you're going to be thinking about binary logical relations. Examples of using logical predicates or unary logical relations are things like type safety. I can set up a logical relation to show that some E of type tau is type safe, that it will, that a term of that type, if it type checks, it will not get stuck when you run it. Another example is to prove strong normalization of simply typed lambda calculus. Strong normalization is a way of saying that all terms in the well-typed terms in the simply typed lambda calculus will terminate. Okay? All right, so that's an instance of this. So let's say termination in simply typed lambda calculus, for instance, or type safety examples of uses of unary logical relations. Here, proving observational equivalence, for instance, in various contexts. And another instance of that is compiler correctness. And actually, let me say something about compiler correctness. You can actually set up logical relations between two terms that don't both belong to the same language. Okay, so you can have a relation that relates source language terms to target language terms. So, the term E and the term E prime could come from two different languages. And actually, for compiler correctness, that's the kind of logical relation that one would want to set up. Yeah?
It seems like that would involve two separate relations, E and tau and E big and tau.
Between E and tau and the E prime and tau?
Yeah.
Yes, exactly. So if you want to think of this as, you start out with a tau in your source language, and perhaps you do a type preserving translation or something of that sort, then what you'd want to think about is, this is my source term. It has type tau, and my compiler translated it to some E prime of type tau plus or tau hat, whatever, translation of tau. And so you set this up sort of, the type of the source level term sort of takes priority, and it tells you what type the other term will have. Yes. Okay. So I'm not going to be setting up those kinds of logical relations where the terms come from two different languages, but I want to show you a pattern where you start to see that this is completely natural, and so that you know how to do it. Okay. Let's see, what else? The other thing that I mentioned before was secure information flow, and this Andrew Myers will talk about a little bit more. But just to give you a sentence or two on what sort of property we want here, well, I'll do that in a second. So Andrew will talk about security type languages where you can essentially label your variables as low security and high security, and then you have a type system which tells you whether or not some high security data leaks into low security outputs. Okay, that's the thing that you want to prevent, and the type system flags that. But now, if you say that I've set my type system up so that it will catch all leaks of high security data into low security observers or outputs, you need to prove something to say that your type system actually does that, right? So what we prove is a property called non-interference. Andrew will explain the details of that. I'm not going to go into it, but the word that I want to mention here is equivalence. Basically, the theorem, non-interference theorem, what it says is that if you have a program and you run it with the same low security inputs, but different low security, sorry, I said that wrong. Let me start over. If you have a program and you have a program P, and let's say it takes a high security input and a low security input, as long as you run it with, you can run it with a different high security input and the same low security input, and you have to be able to get the same low security outputs. So a low security observer should not be able to distinguish the high stuff that you sent in, should not be able to tell the difference looking at the outputs of the program. So it's a form of equivalence. It's a more sophisticated form of equivalence because you have to take into consideration the level of your observer, which is this L here. Anyway, Andrew will get into all of that. But again, the sense that I'm trying to give you guys is all sorts of forms of equivalence, that you want to prove, and you'll find this in many, many different settings. And in my last lecture, I'll give you more examples just to give you a feel for the wide variety of places where these logical relations can be used. Okay, so let me give you a bit more detail on my plan. So today I'm going to talk about strong normalization of simply typed lambda calculus. The fact that all well-typed terms in the language, when you evaluate them, they will terminate. Evaluation will terminate. Okay? Strong normalization for simply typed lambda calculus. All right. I'm starting with this because this is basically the first logical relations proof that most people will encounter, and I want you guys to have encountered it if you haven't seen it already. And what I'm going to do is I'm going to stick to a very standard presentation. Basically the presentation that you will find, give or take, just with a tiny tweak or two, that you will find in Benjamin's TAPL, Types in Programming Languages, Chapter 12. Have that memorized. Okay, but starting tomorrow, I'm going to switch notation on you a little bit. All right, and I'm doing this very, very intentionally because I want you to be completely comfortable with understanding the setup of logical relations and being able to, you know, sort of read papers with one notation or the other and just get the essence out of it. Let's see if we manage to achieve that. But all right, so tomorrow we're going to do type safety using logical relations. And again, this is going to be a unary logical relation, right? Because termination, proving strong normalization, that's a property, it's a unary property. And type safety, again, that a term that type checks will not get stuck. That's also a unary logical relation. And what I'll do is I'll start off doing, you know, showing this for the simply typed lambda calculus, and then I'll add recursive types. Okay? And that'll lead us to some very interesting territory. Basically, logical relations, historically. I said that, you know, you set these up so that you say if E has type tau, you set it up in a way that, you know, for every type tau, you want to show that you want, you basically classify which terms of type, when terms of type tau have the property P. Okay? So this is set up by induction on types. The whole definition is done by structural induction on the type tau. Okay. This works fine, and historically it was great, but it was always restricted to sort of very simple settings where you didn't run into problems and various circularities that come up, like, let's say, when you have recursive types. Because what happens when you have recursive types? When you have recursive types, you can define things like lists and trees and so on. And there are interesting problems that come up with, you know, making sure that this definition remains well-founded. So we'll talk about that tomorrow. So this will be my way to get into how do you have to set up logical relations when you have these more advanced type features. And we'll start with recursive types, and I'll show you step index logical relations. All right? Step indexing has been used. Step indexed. Step indexing is a form of logical relations that's been used with a lot of success in many, many different settings. Basically, anytime you run into certain forms of circularities, this comes in handy. Okay, so we'll talk about that, and then I'll start talking about observational equivalence, how you use logical relations to prove observational equivalence. And here we'll talk about, you know, are people familiar with parametricity, representation independence, at least the terms? Yeah, I see some nods. Okay, good. So we'll talk about those notions here. So we'll start talking about abstract data types and so on. And then, finally, we'll talk about mutable references. Mutable references, as in when you have references in your language, you have dynamic allocation, you can allocate memory on, and you can update it. And these here we'll talk about ML style sort of references where, you know, a memory cell always contains a value of the same type throughout its lifetime. All right, and this leads to some really, really complicated issues. But we'll see that the step indexing trick just sort of, you know, manages to fix all the problems that come up, in a sense. And that'll be where we stop. But I think that by the time we get over here, you'll have a very good sense of the setup, and you'll be prepared to, you know, read all sorts of latest research papers and so on, even if they're much, much more complicated than what we've covered here. All right? Okay, so let's get into it. Any questions? All right. So let me pull this down. Actually, let me pull the other one down. So here's the simply typed lambda calculus. All right, hopefully you're all completely familiar with this. But let me just kind of go through Okay, so simply type down calculus with booleans added. Okay, so we have booleans and we have functions, right? Tau 1 or tau 2. Expressions in the language include true, false, if then else, and of course variables, abstraction, application, right? Okay, we're going to look at a call by value lambda calculus, all right? So here are my value forms, true, false, and lambdas. And I've basically defined the operational semantics by giving the usual Felizen style evaluation context. All right. So this is called by value. So in particular, notice here that when you have application, you evaluate here first, and when that's gotten down to a value, then you evaluate in the argument position, and so on. All right, and here are my reduction rules. So if true, that steps to E1. If false, then that steps to E2. The application case, app case, you have a lambda, it's a value, steps to E with B for X, right? Okay, just getting you familiar with my style of writing things in case it's different from anything, from what's been going on before. All right, and then we have evaluation context here to essentially to define the evaluation order. So we need this rule in order to lift the reduction rules up to the level of full expression. So if you have an expression E that steps to E prime, then we can lift it up to evaluation context using this, right? Okay. Let's look at typing rules. All right, so the form of the typing judgments is going to be that E has type tau under environment gamma. Gamma is a mapping from variables to types, tau. Let me mention a convention. I'm always going to whenever I write gamma comma x colon tau, I'm going to interpret the gamma to mean disjointness. Okay? So whenever I write something like this, that means that x does not occur in the domain of gamma. All right? Just makes things easier. Okay. So true and false have type bool, if then else, the usual rule. Variables, you have to make sure that x is mapped by gamma to tau, the usual function and application rule. Right? Okay. So what do we want to do? We want to prove strong normalization. What is strong normalization? It is the property that if some expression E has type tau, using these type checks, using these typing rules, and let me put an empty context here, then E terminates. I'll use this notation. Let me define abbreviations here. So this means that E evaluates all the way to a value V, and basically it's just sort of another way of writing that E takes a whole bunch of steps and gets to value V, right? Okay. And if I write this and omit the V, then basically what I mean is, sorry, not for all. It means that there exists a value V such that E evaluates to V. All right? Okay. So here's the theorem that we want. Now, I'll let you stare at it for a second. Yeah?
It seems like instead of strong normalization, because you are saying there exists a pathway value instead of that all paths.
No, weak normalization is when all paths to normal forms, all paths reach the same normal form. So if E evaluates to V1 and E evaluates to V2, then V1 and V2 are the same normal form. Strong normalization is where you say that it must terminate. So this says that if E has type tau, then there exists a value V such that E reaches V. So evaluating E will always reach a value.
Okay, but in this case, it's deterministic anyway. But my point is that strong normalization is typically that each reduction path you can possibly take terminates, right?
No. Oh, yeah, sorry. Yes, that each reduction path you can possibly take terminates, yes.
However, here you only have one, so it doesn't matter.
Yes, exactly. Deterministic. Yes, I was going to make that one.
Okay.
Okay, so evaluation here is deterministic, right? The evaluation order is deterministic. There's no non-determinism in this language. So what does that mean? In particular, that means so this is something we rely on in the proof a bit. So in particular, a consequence of that is that if E diverges, then it can't be the case that sorry, if E converges, then it can't be the case that it also diverges, right? You could easily reason through that. Fair enough? Okay. All right. Okay. So if I were to ask you to just go off and prove strong normalization, there's the statement of the theorem right there. If E is well typed, E has type tau, then E terminates. You want to take a stab at it? How would you prove that? Induct on the derivation, all right. Okay. And induct on the derivation. So, okay, so anyone want to sort of think this through, what might happen? So if we induct on the derivation, let's see, we have the true case and the false case. Clearly, those terminate, right? If then else, all right, so we'll apply our induction hypothesis. We know that E terminates, okay, gives us back a Boolean, and we know that E1 and E2 terminate, so, okay, the if then else case should go fine as well, right? Maybe, for those who are kind of following this rough thing. Okay. What about the, okay, let's do the lambda case. Does lambda terminate? Yes, it's already a value. Great. How about the application case? If we were just inducting on the derivation, so what do we get from our induction hypothesis? So we're trying to prove that E1 applied to E2. So we know that E1, E2 has type tau. And, you know, the typing rule tells us that E1 has type tau2 arrow tau, E2 has type tau2. Okay, we're trying to show that E1, E2 terminates. By the induction hypothesis, we know that E1 terminates and that E2 terminates. Now what? What? You would switch to a different proof method, exactly, right? Okay, so what just happened? Well, if E1 terminates, then it has to, it's a function type, all right? So it has to be a lambda of some form. E2 terminates, let's just call it, it evaluates some sort of V2. So now we still have to show that E1 applied to E2 terminates. That means what's happened so far, we've taken a bunch of steps. E1 has become turned into this, you know, has evaluated to this lambda. Lambda has gotten applied to a V2. So after a bunch of steps, we're here. But now we have to show that E with V2 for X terminates. Still have to show that, right? And now there's nothing more that our induction hypothesis gives us. We were doing induction on the typing derivation. Or you can think of it as induction on the structure of E, on the size of E. These are all sort of equivalent ways of saying the same thing. But basically, our induction hypothesis here isn't strong enough. All right? And that's where logical relations come in. Basically, at its core, logical relations are a way of strengthening your induction hypothesis enough to get a lot of these properties of interest through. And the problem case will almost always be, you know, something to do with the lambda form, with functions. Not always. There are more advanced features that complicate life too, but at least for starters. Okay, all right, so okay, just wanted to make sure I hadn't missed anything. All right, so what we're going to do is define a predicate, a logical predicate or a unary logical relation. So I'm going to call it Sn tau. Okay? So the way to read this is some expression E of type tau belongs to this set that I'm going to define called Sn for strongly normalizing. Okay? All right. We're going to do this by induction on the structure of the type tau. All right, so what are our cases going to be? Actually, let me just read. What types do we have to consider? Up there, my types are Booleans and tau1 are tau2. So I'm going to have two cases. All right, so for Booleans, we want to say that E, an expression E of type bool, is strongly normalizing. So what we want to do, and what you generally want to do for most logical relations, is you want to set up this relation or this predicate so that it satisfies three different conditions. All right? The first thing that you want to say is that you want to say that E has this type. So in general, let's just talk about this for some arbitrary predicate P. So usually we define something like this. We want, in the definition, we want to make sure that three conditions are satisfied. The first one is we want to say that E should have type tau. Okay? We want to build this condition in. You can also set up untyped logical relations, slightly separate topic. We'll talk about that later. Okay. The second thing you want to do is you want to say, you want to define this predicate so that so that it requires that E has the property of interest. Okay? In this case, the property of interest is that evaluation of E must terminate. That's the condition we're interested in. Okay, so let's just keep that in mind, and we'll go back and build the definition in a second. And then there's a third condition. So this condition basically says this is the part where you need to, what we just saw in our attempted proof of strong normalization was that we didn't have a strong enough induction hypothesis. All right, and why wasn't it strong enough? In a nutshell, it wasn't strong enough because it didn't capture something about what happened at the elim form for functions. The elimination form for functions is application, right? Someone gives you a function. What do you do with it? You apply it. Okay? But when you apply it, something happened, right? We had a lambda term. It was being applied to a V2. And then we needed to know something about the body of the lambda after the beta reduction, right? We needed to know something about how that behaved. So backing up for a second, this condition that we want needs to say that membership in the relation is preserved by evaluation of elim forms. It's preserved by the elim forms, okay? And we'll see that this is not always sort of built in, but okay, I'll get to that in a second. Logical relation is preserved by evaluation of elim forms. Okay? And for us, what that's going to mean for this particular thing is that when you, let's say in the case of lambda, when you do an application, you want the expression to still belong to the logical relation. So let's get to that concretely. All right, so we want to build this. I have an expression. I want to say that this expression at type bool is strongly normalizing. So let's build it with all of these conditions. So we're going to say that E must have type bool. So E is strongly normalizing at type bool. If E has type bool, that's condition one. If the E has the property of interest, so we want it to be the case that evaluation of E terminates. And by the way, here E is a closed expression, so keep that in mind for now. The relation that we're building is a relation on closed terms. It doesn't have any free variables. Okay, we'll generalize it to free variables later. All right, so that's condition two. Condition three, the logical relation is preserved by the evaluation of elim forms. What's the elim form for bool? If, okay. But I'm not going to build anything more into this. And I'll come back to that in a second. When we did our naive proof earlier for using just induction on the structure of the derivation, if went through just fine, right? Nothing went wrong there. Keep that in mind for a second. Okay, so we're done with bool. Now let's talk about functions. When is an expression of type tau1 or tau2 strongly normalizing? Well, it better have the type tau1 or tau2. It's an expression. It's not a lambda yet. It better terminate. And this is where we need a third condition about the elim forms. What we want here is, basically we want to say that given an arbitrary, let's call it E1, such that E1 is a strongly normalizing expression of the arguments type, it better be the case that when we take E, our expression of function type, and apply it to this E1, we get a strongly normalizing expression at the result type, tau2. Now we'll see this in a proof for a second, but basically what we're trying to build in is this third condition. If you give me an input, an argument that is strongly normalizing, then applying the function, essentially, to that argument will be strongly normalizing as well. So we're building in this requirement into the definition. Okay. Now, is this definition well-founded? We were defining it by induction on the structure of the type, right? So here, this looks perfectly well-founded. Here, when we define it for tau1 or tau2, we're defining the set Sn, essentially, right? The set of expressions Sn at the type tau1 or tau2. But in the definition, we only use the definition of Sn at a smaller type, tau1, and a smaller type, tau2. So yes, this is well-founded, because these types are smaller than tau1 or tau2, right? Okay. All right. So now let's see. So one thing that I want to let's mention that. I'm just going to erase this. Is that all right with everyone? Okay. Okay. So notice we've just built this relation. Now, the theorem that we want to prove is still the one up there, right? That if E is well-typed, then it terminates. Evaluation terminates. Okay. So how does this definition of Sn fit in? Basically, what we're going to do is we're going to do the proof in two parts. We're going to show that if E has type tau, a closed term, then it is strongly normalizing, or it belongs to the set that we've just built. All right, so this is going to be part one of our proof, or one lemma. And the other lemma that we're going to prove then is that any term E of type tau that is strongly normalizing, or rather, whenever E belongs to this set Sn, then if you evaluate it, it will terminate. Yeah.
Yeah, because it's a condition.
Precisely. I just want to make it completely obvious, right? So what he just said is that proving 2 is a no-brainer, essentially, right? Because we've built it into the definition. I mean, look at it. How would we, let's prove 2, just to convince ourselves completely, all right? So how would we prove 2? Well, let's prove it by induction on tau, all right? We have two cases. We have a case for Booleans. We have to show that E terminates. Oh, the definition tells us that it does. So we're good, right? There it is. Okay. Now we have to consider the case where tau is a function type, tau1 or tau2. Right? We have to show that the expression terminates. Okay, let's go look at the definition. Oh, right here. Okay, so basically, this is trivial. We've built our definition so that the property of interest is built in by definition. So really, all the work is in this first lemma right here. We have to show that every well-typed term, every well-typed closed term at least, of type tau belongs to the set Sn at type tau. Okay? So let's take a look at how we would do that. Yeah?
What part of what you're doing is in the semantical part, and what part is it in the proof? Because you defined this Sn, you said, well, this is the condition.
Yeah.
Are those semantical conditions? Or
Semantic how? In what sense are you using?
I mean, you wanted to mean something, but then you said, well, emerges, right? So
Okay, so, well, let me try to pick us out of that. Okay, so what I'm building, if you think about it in a semantic sense, right? I'm building a set or a model, right? I'm calling it the set Fn. And I want that set to be inhabited by all terms that terminate, right? Essentially, that's the semantics for now, you know, of what the set Sn is. Okay, but basically, all Sn is just sort of a way of strengthening our induction hypothesis so that we can prove that any well-typed term does, in fact, belong to the set Sn at the appropriate type. Does that make sense? Every well-typed term must belong to this set or this model, you know, that we built. Okay? Yeah.
So can I understand? Here is to define some logical relations which is as strong as the one that we want to prove, then prove that one step. So,
if you want to define, say that again.
so here is to define some logical relations which is as strong as the one we want to prove, which is determinate, then prove that one step.
Yes, exactly. I mean, and you need to go through this condition because it allows you induction hypothesis. Okay? Because when we tried to prove this directly going from here to here, we failed because our induction hypothesis wasn't strong enough. Okay? And this will become a little more clear as we step through the function case and of the proofs. Okay. But we still have another problem. Okay. We have defined when closed terms are strongly normalizing, right? And the theorem that we're interested in is about closed terms. If you have E, it's a closed term of type tau. It doesn't have any free variables, right? It type checks under the empty environment. Then we want to show that it terminates. Now, here's the